The topic of this lesson is finding derivatives with the limit definition. So first we're going to talk about what a derivative is and what is the limit definition of a derivative, and then use that definition to calculate a few examples. So let's start with what a derivative is. This is the basis of the entire first half of calculus. We've talked about limits, you've learned how to calculate limit, and that's necessary for what we're going to do here. But this is really where we start talking about the first half of calculus, called differential calculus. And that involves calculating these things called derivatives and using those in their applications. But first, let's just start with what a derivative is. Functions have derivatives. The derivative of a function, it's a different function that will take x as its input, and the output will be the slope. And I'll show you a picture on the next slide that illustrates that a little better. First, I'm going to show you some notation for derivative. F of x is notation for just function. F prime of x is how we would say this. Put a little apostrophe between the f and the parentheses, and this would be read f prime of x. If the function's given as y equals, then we could do the same thing, do y prime, and then another common one is dy over dx, and we can talk about the meaning of those, but for right now these are the three common ones. You should see any of these three symbols and recognize that that means the derivative of a function. Okay, so in my own words definition, I said that the derivative gives us the slope if we input an x. If you just graph a function, you are inputting x's and outputting the y values that correspond to those. For example, the point 39 is on this graph right up here because the function is f of x equals x squared. If I put 3 into that function, I get 3 squared, which is 9. So this parabola is just a collection of infinitely many points all next to each other that all represent the function f of x equals x squared. The derivative, and you don't know how to figure this out yet, but the derivative of x squared is 2x. That's why my notation f of x equals x squared, f prime of x equals 2x. So this is the first derivative you've seen. We'll calculate it in just a minute. But what it tells me is the slope. So if I input any x value, I'm not going to get the height of the function, I'm going to get the slope of the function at that point. And now curvy lines don't really have slopes, straight lines have slopes, but what we're calculating is the slope of the tangent line. It's kind of like the instantaneous slope, and we can talk about that a little bit more in person. But if you look at this graph at -2, the height of the function at -2 is 4. See this, this blue line over here? It has a slope of -4. It goes down 4 and over 1. If I substitute -2 into the derivative, -2 times 2 is -4. So that shows up because this tangent line, if I move it into place, has a slope of -4. All right? A tangent line is a line, a straight line that just bumps into the graph at one instant point, and it shows kind of the way that graph is pointing at the instant. If I look down here at the bottom, at the vertex of the parabola, it goes through 0, 0. The slope, if I substitute 0 into this derivative, if I put a 0 right here, I get 2 times 0 is 0. Well, remember, a flat horizontal line has a slope of 0, so I can see this horizontal tangent line. It just goes flat across the bottom. At that instant, the graph is moving straight across. Okay, and then finally, this line over here, look at its slope. Its slope is, if I move it into place, it's going up 2 over 1. If I substitute x equals 1 into this function, the derivative, I get 2x, 2 times 1 is 2. So here's that tangent line with a slope of 2. Rise 2, run 1. Rise 2, run 1. So this is all differential calculus is about. It's about finding these derivatives, and these derivatives tell us the slope of a graph at a certain instant. At this case, slope is -4. Down here, slope is 0. And over here, slope is 2. The slope of the function changes just as the value or the height of the function. All right, so let's look at a couple examples of how to calculate a derivative such as this one. Okay, I want you to start by writing this definition down and putting a couple circles around it in your notes. This is the limit definition of derivative. It's got this delta x. We're going to treat delta x just like any other variable, like it's a y, or sometimes it'll be called an h. One of the tricky parts of this is getting used to delta x just being one quantity. And I'll show you a picture later at another time that explains why this function or why this formula works the way it does. But for now, let's just learn how to use it, and then we'll get to the particulars later. But make sure you get this down and memorize it. It's all just based on the slope formula, y minus y over x minus x. But like I said, I'll show you the particulars at another time. Okay, so I've recopied that definition at the top, which you should start each of these problems by doing. And then I've got the example. Now this is the example that we had the picture of, just a simple parabola y equals x squared. I already know my answer is the derivative of x squared is 2x. Let's connect the dots and see how we get from start to finish. I'm going to first just substitute in to the formula using my particular function. So that's going to look like this. F prime of x is what I'm trying to calculate. Remember, when you put the little prime, that means derivative. Delta x approaches 0. That's going to be the same in every problem. The next thing I come to is f of x plus delta x. So what that means is write the function, but wherever you see an x in the function, replace it with x plus delta x. So here's the function x squared, but into that function I have input the quantity x plus delta x. The next thing that happens is minus f of x, and that's just my function, x squared. And the bottom is going to be delta x every time. That doesn't change here on step 1. So the first step, every single time, you write your limit, and you write the function with x plus delta x, and then you write the function itself with a subtraction sign, and now you're ready to go. Next thing we do is just some algebra. We just simplify. And for us, that's going to be squaring out this quantity, x plus delta x. Remember, you cannot square x plus delta x just by distributing this. Doesn't work that way. You have to write it out twice, and you probably learned the acronym FOIL. We're going to FOIL it out. We're going to multiply these two binomials. So when I do that, I get x squared plus 2x delta x plus delta x squared. I combined that outer and inner in one step. Each one of those was x delta x, so I put those together to get 2x delta x. So I just did that off to the side to keep my steps simple over here. My first thing in this big fraction is x squared plus 2x delta x plus delta x squared. So all I did was simplify the parentheses. Now comes minus x squared, and delta x is on the bottom. So here's what should happen. What you should notice is anything without a delta x in it at this point should cancel. See this x squared right here, this negative x squared right here? Those are going to cancel each other out. It simplifies things. The problem, by the way, with taking this limit is you can't substitute 0 into this delta x. That's what the limit, we're trying to take the limit as delta x goes to 0, but I can't sub in and make that delta x into 0 because the denominator can't be 0. So we're using some of our limit taking strategies. In this case, it's going to be factoring and canceling. Once the things with no delta x go away, everything has a delta x. So on the top, if I factor that delta x out, I'm left with 2x plus delta x. All right, this term here, if I take away delta x, I'm left with 2x. This term here, I take away one of those two delta x's, I'm left with another one. And the good thing that happens now is these two delta x can cancel, and I'm left taking the limit as delta x goes to 0 of 2x plus delta x. Now we're at our simplest scenario where we just substitute 0 in for delta x. This becomes 0, and my answer is just the 2x. Okay, so we knew that 2x was the derivative of x squared. This is the steps that would get us to that point. So here's another parabola. It's not as simple. It's not just centered at the origin. I would encourage you to try to repeat the process we just did. I know this is just the second try, but try to pause your video, complete that process, see if you can come up with the derivative of this function, and then restart and see the steps. This derivative is going to be called y prime because our function was called y. It doesn't really matter whether it's y prime or f prime or dy dx, not an issue. But if it's given as y, I'll call it y prime. The first thing is the limit as delta x goes to 0 every time. I'm just going to write that. The next thing I do is write the function, but replace x's with x plus delta x's. So that'll look like this. Three x becomes 3x plus delta x, and 4 is just 4. Next thing I have is minus the original function. I want to make sure to put parentheses here because this entire function needs to get subtracted. And if I'm not careful there, I will forget that this negative applies to everything in these parentheses. And don't forget delta x on the bottom every time. Okay? So, next, I want to just do some algebra. I want to do some simplifying. I want to square stuff out. I want to distribute. I want to see that everything with no delta x in it goes away. Keep this limit. The last thing we're going to do is evaluate the limit. We can't do that until we get this delta x on the bottom fixed. When I square x plus delta x, I get what I got a minute ago on the last screen. When I distribute the 3 into the second set of parentheses, I get this. And then I'm just going to go ahead and distribute the negative into the last set of parentheses, which will look like this. So now see what happens. Everything with no delta x in it goes away. X squared, negative x squared. Plus 3x, minus 3x, plus 4, minus 4. All the terms that are left, which would be this one, and this one, and this one, have delta x's in them. I'm going to factor that delta x out and cancel it with this guy down here. When I factor that delta x out, I'm left on top with 2x plus delta x plus 3, delta x on the bottom. The reason I couldn't just take the limit in the first place was this delta x on the bottom. I've solved that problem because now there is a delta x on the top to cancel, and I'm left with just taking the limit of what's left over. Well, when you take the limit of what's left over, you just make any delta x's go to 0. So this delta x goes to 0, it disappears, and my answer is 2x plus 3. All right, so we would say that the derivative of x squared plus 3x plus 4 is 2x plus 3. This function, 2x plus 3, will give me the slope of this parabola at any x value. All right, don't forget what a derivative does. It gives you the slope of this, of the tangent lines of that parabola at any x value. All right, we're going to wrap it up with one more example, a little bit different, not a parabola, so it'll work differently. And when we had limits to take, we had different strategies, and this is going to bring up another one of those strategies. We're not going to change the fact that we start with the limit definition. The limit as delta x approaches 0 of, first thing is the function evaluated at x plus delta x. I'm going to go ahead and get my big fraction bar with delta x on the bottom. On the left on the top is the function evaluated at x plus delta x. That's going to look like this. The fraction 1 over x becomes the fraction 1 over x plus delta x because I replace x with x plus delta x. Then I just do the function, which is just 1 over x. Now, I cannot substitute delta x directly into this because I have a 0 in the denominator. I would end up with a 0 in the numerator also, but that's a problem. I also can't fix this problem in the same way I fixed the parabola examples, I'm going to fix this problem and be able to take this limit by getting a common denominator and adding the fractions together and then canceling some stuff out. So in order to add these two fractions on top, their common denominator is just the two denominators multiplied together. So this left fraction needs to be multiplied by x over x. And this right fraction needs to be multiplied by x plus delta x over itself. This is going to allow me to add the two fractions on top. And this is a strategy we did when we just solved limits. It's just now that this is the definition of derivative, that limit really means something important. Just getting my two fractions with common denominators. I have x over x times x plus delta x minus x plus delta x over x times x plus delta x. Haven't done anything yet. I haven't really added them yet. I've just got the common denominator in place. Now I'm going to add those fractions. And you should see stuff start to quickly cancel out in your derivative. Your answer gets more and more clear. When I add the two fractions on top, I get x minus delta x. I'm going to go ahead, like I did before, and distribute this negative. That's an easy one to leave out. Don't forget that that negative sign applies to both of the items in the parentheses. So there's the common denominator, and I'm only working with the top so far. This is a fraction within a fraction, and the denominator of the whole thing is still delta x. So I added these two fractions and got this. Well, those two x's, you can see, go away. So move up here. Here's where we stand. The limit as delta x goes to 0 of negative delta x over x times x plus delta x. And all of that is over delta x. Instead of writing all of that divided by delta x, I'm going to go ahead and multiply it by 1 over delta x because it just visually makes more sense at that point to get rid of those two. All right, I could do it down here. I could say, okay, I've got delta x here and delta x here, and those cancel, but that little fraction within a fraction setup's kind of tough to see sometimes, so I'm going to get rid of it by changing the division to multiplying by the reciprocal. Now here's what's left. I've got negative 1 from the negative sign and the 1, and x times x plus delta x. All right, now I'm not going to get 0 if I let this delta x go away. Since delta x approaches 0, pretty much just ignore this part and see what's left over. Negative 1 on top, x times x on the bottom, x squared. So all of that tells us f prime of x, the derivative of f, is equal to negative 1 over x squared. Okay, so make sure you know what that function does. If I input any x into the original function, it tells me the height of that function. If I input an x into the derivative of that function, it tells me the slope of the tangent line of the graph at that x value. And that's going to wrap up our discussion of finding derivatives with the limit definition. This is an important one. Make sure you get this definition memorized and do all your practice problems. This one's going to stick with you for a while.